What is the shortest possible program that produces a given output? This deceptively simple question leads to one of the deepest ideas in all of mathematics and computer science. In 1965, Andrei Kolmogorov asked, "Can we measure the information content of a single object? Not a random source, not an ensemble, but one specific string of bits?" His answer was elegant and disturbing. Yes, we can define it. The Kolmogorov complexity of X is the length of the shortest program that produces X on a universal Turing machine. But here's the catch. We can never actually compute it. This uncomputable quantity.
Let's make this precise. The Kolmogorov complexity of a string X, written K of X, is defined as the minimum over all programs P such that U of P equals X of the length of P. Here, U is a fixed universal Turing machine. The program P is a binary string. It takes no input, it simply runs, produces X as output, and halts. K of X measures how compressible X is, in the most fundamental sense possible. Consider two examples. First, take the string of 1,000,000 zeros. Despite being 1,000,000 bits long, we can describe it with a tiny program. Print 0 1,000,000 times. Its Kolmogorov complexity is roughly log of 1,000,000, about 20 bits. Now consider a string generated by fair coin flips. No pattern, no structure. The shortest program that produces it is essentially print this exact string, followed by the string itself. Its Kolmogorov complexity is approximately equal to its length. This is the key insight. Structured data is compressible, random data is not. Kolmogorov complexity separates the two, measuring the intrinsic information content of individual objects.
You might object. Doesn't K of X depend on which programming language we use? A Python program and a C program for the same output have different lengths. This is where the invariance theorem comes in, arguably the most important result in algorithmic information theory. For any two universal Turing machines, U1 and U2, the difference between K sub U1 of X and K sub U2 of X is bounded by a constant C that does not depend on X. In symbols, the absolute value of K sub U1 of X minus K sub U2 of X is at most C. Why? Because any universal machine can simulate any other. If U2 has a short program for X, then U1 can run a simulator for U2, which has fixed, constant size, followed by that program. The overhead is at most the size of the simulator. For short strings, this constant might dominate, but as strings grow longer, the constant becomes negligible. Kolmogorov complexity is well defined up to an additive constant. This is why we can talk about the complexity of a string, not just its complexity relative to some specific language. The choice of reference machine washes out.
Here is the disturbing truth. Kolmogorov complexity cannot be computed. There is no algorithm that takes a string X as input and outputs K of X. The proof is a beautiful application of the Barrier paradox. Suppose we had a program compute K that computes K of X for any X. We could then write another program, find complex, that searches through all strings in order and returns the first string X whose Kolmogorov complexity exceeds some threshold n. This program, find complex, has a fixed size plus log n bits to encode the threshold. But the string it outputs has complexity greater than n. For large enough n, we have a short program producing a string with high complexity, a contradiction, since the program itself is a short description of that string. This is essentially the same structure as the Barrier paradox. Consider the smallest number not definable in under 100 words. That sentence defines the number in under 100 words, contradiction. The uncomputability of K of X means we can never know the true complexity of a string. But this doesn't make it useless. Upper bounds on One of the most powerful applications of Kolmogorov complexity is the Incompressibility Method, a proof technique that leverages the existence of incompressible strings. Here's the counting argument. There are exactly 2 to the n binary strings of length n, but there are fewer than 2 to the n programs shorter than n bits, at most 2 to the n-1 to be precise. By the pigeonhole principle, at least half of all strings of length n cannot be compressed at all. They have k of x at least equal to n. These are the incompressible or random strings. The incompressibility method works like this. To prove a lower bound on some computational quantity, assume the input is incompressible. Since incompressible strings have no exploitable structure, any algorithm must essentially process every bit. And since most strings are incompressible, the bound holds for a majority of inputs. For example, consider comparison-based sorting. Take an incompressible permutation of n elements. Any sorting algorithm must make enough comparisons to distinguish this permutation from all n factorial possible orderings. An incompressible permutation requires log of n factorial bits to specify, giving us the classic n log n lower bound, derived without any adversary argument.
How does Kolmogorov complexity relate to Shannon entropy, the other great theory of information? They answer fundamentally different questions. Shannon entropy, h of x, measures the average information content of a random source. You have a probability distribution, and h tells you the expected number of bits per symbol needed to encode messages from that source. It's a property of the ensemble, the entire distribution. Kolmogorov complexity, k of x, measures the information content of a single, specific object. No probability distribution required. It asks, how compressible is this particular string? The beautiful connection. For a computable probability distribution P, the expected value of k of x equals h of x plus a constant. On average, the two theories agree, but they diverge for individual objects. A specific string of all zeros has low k of x regardless of the source distribution. Shannon entropy can't tell you about individuals, only averages. This distinction matters profoundly for machine learning. When we train a model on a specific dataset, we care about the complexity of that dataset, not an ensemble average. Kolmogorov complexity is the right framework for reasoning about individual.
Kolmogorov complexity is uncomputable, but its influence on machine learning is everywhere. Start with the minimum description length principle, which we covered in episode 19. MDL says, choose the model that minimizes the total description length of model plus data given model. This is a computable approximation of K of D, the Kolmogorov complexity of the data. The best possible compression of data D is K of D, but since we can't compute it, we work within restricted model classes and optimize L of H plus L of D given H. Every MDL method is implicitly trying to approximate the uncomputable ideal. Then there's Solomonoff Induction, perhaps the most beautiful idea in all of artificial intelligence. Solomonoff's universal prior assigns each hypothesis H a probability proportional to 2 to the negative k of H. Simpler hypotheses, those with shorter descriptions, get exponentially higher prior probability. This formalizes Occam's razor with mathematical precision. Solomonoff proved that a predictor using this prior converges to the true distribution at an optimal rate, regardless of what the true distribution is. It is the theoretically perfect learning algorithm. Of course, it's uncomputable, but every practical learning algorithm, from Bayesian neural networks to large language models, can be understood as an approximation.
Let's step back and see where we are in the series. In episode 19, we learned the minimum description length principle. The best model is the best compressor. In episode 20, we saw that regularization is about limiting the information content of weights. Episodes 21 and 22 explored how complexity rises and falls in physical systems. Now, in episode 23, we've reached the theoretical bedrock. Kolmogorov complexity is the ideal that all these practical methods approximate. K of x answers the question, what is the absolute minimum number of bits needed to describe x? It's uncomputable, a theoretical limit we can never reach. But like the speed of light in physics, it constrains everything. Every compression algorithm gives an upper bound on k of x. Every model selection criterion approximates the